Swayam Prabha. Digital India. Educated India.
Hello everyone. Today we will start our discussion with a very important topic, which is spectrogram. And first let us understand the basics of a spectrogram. What does a spectrogram mean? Then we will discuss the analysis of spectrogram with different numericals. Spectrogram, one, it's a graphical representation. It's basically deals with only periodic fault. It only identifies the periodic fault. Okay, if there is any random unevenness, random variation is there, the spectrogram will not be able to identify. And in periodic fault, as we have discussed, this is the periodic fault, and periodic variation, spectrogram will be able to identify the wavelength of the periodic fault. And once we identify the wavelength, then we can pinpoint the defective component of the machine in the spinning line. So application of spectrogram is that just to identify the defective point. If we see the shape, typical shape of a spectrogram is like this, that we will discuss in detail. And the spectrogram of very even yarn, suppose there is completely even yarn, and spectrogram of very uneven yarn, random uneven yarn, no periodicity. In these two yarns, yarn 1, yarn 2, will not be able to differentiate the shape of the spectrogram, will not be able to make out anything by looking at the spectrogram of very uneven yarn. But once there is a periodicity in the yarn mass per unit length, then only the spectrogram identifies the wavelength. Now how? Let us discuss. So spectrogram, by definition, it's the amplitude of periodic mass variation which is plotted against the wavelength, which will be in x-axis, x-axis, amplitude will be y-axis. Okay, so this is wavelength, and this is amplitude. So this term amplitude, it doesn't mean the extent of variability. Like if you see two yarns, this is one yarn and another yarn with a variability like this. So in these two yarn, if you assume, let me draw it once again, this one, okay. So another yarn with same wavelength, these are the two wavelengths. So literally amplitude should mean the extent of irregularity, not. But as far as spectrogram is concerned, the amplitude means something else. So when we talk about the normal wave, this is one wave. So another yarn which is in red color, it shows that amplitude as far as normal sense is concerned, it's a high. So which is shown here by the yellow color fiber structure. So amplitude in spectrogram doesn't mean the extent of irregularity. It is the number of times a fault of that length occurs. That means number of irregularity. It doesn't mean the extent of irregularity. Normally, in any waveform, we mean the extent of deviation by the term amplitude. The amplitude means that extent of deviation, but in spectrogram, it's the number of time that repeats. Let us consider material is moving through one evenness tester at 400 meter per minute for 2.5 minutes. So that means total length it is traveling, it's 1000 meter. So the yarn, if we consider its yarn, the 1000 meter yarn is tested. Now let us consider three different types of yarn strand. The red color I am drawing here, which is the most irregular type of yarn. There is no repeat. So it is not periodic fault. So it is a totally random variation is there. The second yarn I am drawing, it is of length 1000 meter, which has got periodic irregularity. That means thick and thin places are repeating at constant interval, but here the wavelength is low. So this type of fault normally is generated at the end of the process like at the front roller. The third yarn variation, which is again periodic, which is shown by the blue line, where the wavelength is much longer than the second one, which is in the green color. So, here, so first yarn is irregular yarn, no periodic fault. Second yarn is periodicity is there, but the length here is low, and third one is the periodicity is again there, but the length of periodicity is high. So, here we can see, so two consecutive say thin places, here it is a periodic length, that is a wavelength, and in first yarn, as I have told, here there is no periodicity. So, number of repeats here we can consider as 0. So, there is the number of number of times the fault generated, it should be 0. So, we can consider here N1, that is number of times the fault is generated in case of yarn 1 is 0. So, for second yarn, the wavelength here it is a 1 meter, that means we can see from the diagram here it is a two consecutive thick places, the length here between two consecutive thick places is 1 meter. So, if you see here, so in 1000 meter, the number of times the fault is repeating. So, let us say N2, okay, N2 will be equal to, so N1 is 0 because for irregular there no repeatability, it is a N1 will be 0. So, there is no repeat, but in case of the wavelength green color yarn, the number of repeats will be 1000 by 1 equal to 1000 times, the 1000 repeats will be there. So, this number of repeat here for yarn N2, yarn 2, so it will show up at the y axis. So, the height of the chimney will be proportional to 1000 because it will be very high, and on the other hand, if we see the yarn 3 where the wavelength is 10 meter, if we consider, so here number of repeat will be, so 1000 by 10, it will be 100. So, if we draw the spectrogram here at the length base, so x axis for 10 meter cut length, height will be proportional to 100 here, and for yarn 2 at 1 meter it will be proportional to 1000. So, for yarn 2 the number of occurrence is 1000 times, thousands are the number of faults, and for yarn 3 it is 100. Now, if we see a typical spectrogram, in x axis it is wavelength, y axis is the amplitude. So, if we test the yarn 1 with random unevenness, so number of repeat is 0. So, the spectrogram is not able to identify, but for yarn 2, this 1000, this is a basic spectrogram, this 1000 will be plotted in the y-axis and at the wavelength of 1 meter. So this is the wavelength x-axis, wavelength here it's x-axis wavelength, and the 1000 will be plotted. This is 1000. And in case of yarn 3, there are 100 repeats. So this is 1 meter. Here it's a 100 meter, 10 meter. This is 10 meter. So 10 meter, there will be 100 times. So we can see as the wavelength increases, the number of times it repeats is reducing. So height of the amplitude will be lower always. So this is the reason the shape is in this type of bell type shape, where the lower portion is just reducing while we are going towards the higher wavelength. So this is the basic concept, and this height shows the number of repeats, not the extent. Okay, that means when we go towards the lower wavelength, the height will be more. Okay, but that doesn't mean the extent of irregularity is more. Okay, now two yarns, as I have shown earlier, with the same wavelength, like this is one yarn, okay, another yarn with a low variation. This is yarn A and another one is yarn B. These two yarns, if we test, now let me draw once again. Clearly. So let us now consider two yarns of wavelength, say 1 centimeter. Two yarns of wavelength 1 meter. One meter wavelength, two yarns we are considering. So this is yarn 1. Yarn 1, another yarn of same wavelength, so this yarn 1 green color, yarn 2 blue color. So yarn 1 and yarn 2, they have the same wavelength, but extent of defect is much more. This normally occurs due to, say, eccentricity. One roller is having very small eccentricity. Another roller which is forming yarn 1 is having very high eccentricity. But the roller diameters are same. Due to higher eccentricity, the extent of irregularity is more. But if we test, and the wavelength of these two yarns are 1 meter. If we test these two yarns and number of waves will be 100, number of repeats will be 100, so 1000, 1 meter, thousand times it's repeating. So what will be the location of wavelength or shape of the spectrogram? So location will be 1 meter, because 1 meter is the wavelength, and number of repeat in both the cases are 1000. So for yarn 2 with lower extent, it will also coincide with that same height. So if you superimpose the spectrogram of yarn 1 and yarn 2, they will look same, which means the spectrogram is not able to identify the extent of irregularity. But looking at the, if we can identify the defective roller, okay, then that analyzing the defective roller, we can get the idea. But this extent of variability, extent of defect, we can get from the diagram that I have already explained. So the diagram of this yarn 2 with the blue color will be like this. This is the diagram. So this will be wavelength 1 meter, and diagram of yarn 1, which is with green color, it will be with a higher text. This will be the difference. So if we want to know the extent of variability, we can refer to the diagram we have discussed. But if we want to locate the fault, we can refer to the spectrogram. Spectrogram pinpoint the location, but diagram will give the idea about the wavelength. Okay, so this is the overall concept of the spectrogram, and with this concept we will discuss the different aspects and how to use the spectrogram for our day-to-day application. So from the speed at which the yarn is running, the capacitance type, through the capacitance type sensor, the frequencies are converted to wavelength. That means the thick and thin places that we record through the capacitance type sensor, and the frequencies are recorded and plotted into a finite wavelength steps. Now try to understand what is happening. Suppose this is the capacitance type sensor. This is a parallel plate capacitor. Now the yarn is moving. The yarn is moving, red color. We know this is the length of the capacitor is 1 centimeter standard. Normally keep 1 centimeter. And when it's moving, so within this capacitance plate zone 1 centimeter, it's sensing the mass. Although it's proportional capacitance value, so it identifies the mass value, and depending on the speed, so it can identify the wavelength. So depending on the change in mass, it's identify the wavelength. Now suppose this particular yarn, when it's moving, this is the yarn. Now this sensor will not be able to identify any variability less than 1 centimeter. 1 centimeter is the sensor size. Now let me explain this in detail little bit. Suppose this is a sensor. This sensor is 1 centimeter. One yarn ideally, so imagine one yarn with a variability, periodic variability 1 millimeter only. So 1 millimeter, so within this zone there will be 1 millimeter wavelength, there will be 10 waves. So it will not be able to sense. So effectively what happens in our spinning system, the roller diameter, if you assume of 1 inch, so 25.4 centimeter, and circumference of the roller, even if it is front roller, circumference will be pi multiplied by 25.4 centimeter. This is 79.7. So that is the minimum wavelength due to the eccentric front roller. So that will take care. So that the 1 millimeter wavelength is not possible. So one yarn is moving long wavelength. So this sensor continuously sensing the mass per unit length. Now it is sensing, so here suppose this is the capacitance value, so it's sensing the mass per unit length gradually increasing, then again it's reducing, even if it is say periodic fault, reducing and again reaching to a certain point. And as soon as it's identifying the time for after which time the same capacitance value is reaching, and from the speed of the machine, it is identify the okay, there is one periodic fault has gone. So in spectrogram, it has calculated the periodicity, wavelength. So this is the particular wavelength. Say that suppose this is say 10 meter. So 10 meter, it is pointing. Now this is one wave, one block piece. Again it's continuing. Next block, next block, next block. So if it is testing 1000 meter, so there will be say 100 such. Okay. It has also been observed that a spectrogram can have multiple peaks. This is called peaks or chimney. Multiple peaks. Suppose along with the 10 meter, another fault has occurred in 1 meter, because it's not necessary only one roller will be eccentric, one pinion teeth will be broken. So that can be multiple faults. So if it is 1 meter, so there will be 1 meter here, again there will be repeat. So if for 1 meter there will be 1000 such blocks. And it will make one histogram. Okay. So this is the basic understanding of spectrogram. So here we plot a histogram automatically, and you can see here there are histograms. Spectrogram of say a draw frame slide. So the defect is at the draw frame. Spectrogram, if you test, suppose there is a defective roller. And another thing we can see here, in spectrogram x-axis, the axis is in logarithmic form. And a defective roller or defective pinion, due to some jerk, the periodicity has occurred. Here the periodicity has occurred at say 14 centimeter. This is 14 centimeter. Now when we stretch it in the roving frame, we have observed typically it's a say 90 centimeter. So due to the draft, so how much draft has been incorporated here? 6.42 draft was given in the roving frame, and it has been stretched. That means if the draw frame wavelength is such, the roving frame will have 6.42 time stretch was there, so wavelength has increased. Okay, and we can see as the wavelength increased, so number of times it occurred, it has reduced, so height has dropped. Always we will see when the wavelength is less, so height will be more, and wavelength is more and height will be less, and it is further stretched to several times. Suppose it's a 18 meter, so 90 centimeter, 18 meter, so 1800 by 90, 20. So it is further stretched in the ring thread. So repeat, number of repeats has reduced, and that's why height is reduced. Now the shape of the basic spectrogram is this. This is the shape of the basic spectrogram. So basic spectrogram shape is this. So with reference to the basic spectrogram, how much it's exceeding that chimney, that using that with the ratio of the basic height and how much it's exceeding, that will show the significance of the height. Whether, suppose which one will be significant. So there are peaks. This is one peak. Another peak we can consider this one, another. There may be many other peaks, small peaks, but these peaks are, we have to see whether they are actually significant, whether they will affect the product. So that will depend on the ratio of the basic spectrogram and how much it's exceeding to that ratio, that basic spectrogram. So that ratio, if we see, then we will be able to understand whether it's a significant or not. So it helps in locating the fault generating point. And also due to drafting wave, sometime what we get, suppose this is the basic spectrogram, and if there is a clear peak, then we will, this is due to the faulty machine component. And also the periodic fault sometime occurs due to drafting waves. So drafting waves, in the drafting waves you will see there will be spreading of humps. Spreading of humps are there within a certain zone. Then we will identify it as there is a problem of drafting. So fiber length and setting, this adjustment should be there. So typically it has been observed, typically the wavelength is within the range of 2.5 to 3 inch for cotton. And as I have mentioned that there is a theoretical spectrogram, and which is given by complex relationship So that we don't need to discuss at this point. So you can see the shape. This is the shape of natural funnel where length is variable, and this is the shape of spectrogram with a cut plane, certain fiber cut plane, equal fiber cut plane. So here the basic spectrogram, theoretical spectrogram, and due to the defect, periodic fault, the chimney occurs above that. Okay, for normal fiber, normal variability, this is a type of spectrogram. Now try to see the applications of the spectrogram. Now this is a figure. This is a drafting arrangement, 3/3 drafting arrangement of a ring frame, which produces 40 Ne cotton yarn from 1.212 Ne roving. So roving is fed here at the back with 1.212 Ne, and we are getting yarn of 40. So considering there is no twist contraction, total draft will be 40 yarn count by roving count. It will be approximately, it will be 33. So 33 is the total draft, and the break draft is given. So break draft is draft at the back zone, it's 1.115. So front zone draft between middle roller and front roller, front draft will be 33 by 1.115. It will be 29 point, typical 29.5. So front draft is 29.5. So what we have to do, we have to identify the position of the peaks in the spectrogram of yarn if pinion D is defective. So we are testing the yarn. So yarn spectrogram we have to identify. If the pinion D is defective, and then if pinion F is defective and pinion back roller and mid roller. So pinion D is defective, pinion D defective, pinion F is defective. This is the pinion F, and back roller is defective. This is the back roller. So pinion D, it's defective. Pinion F is defective. This is a pinion F. Back roller is defective, and middle roller is defective. At 4 conditions we have to calculate. Considered in case of pinion, the defect is due to broken tip. So one tooth may be broken, and in case of drafting roller, the defect arises due to eccentricity of the roller. And here the values in the parenthesis are the number of teeth in the particular pinion, and in case of roller, these are the diameter So for back roller diameter is 25.4, middle roller 23 and front roller it's a 25.4. So 3/3 drafting arrangement. Now let us try to solve. So pinion 1, when pinion 1 is defective, so pinion D is defective in case of numerical 1. So 1, that the pinion 1 is the source of drive. So this drive, assuming the source drive is not erratic, there is no periodicity. So for one revolution, so one tooth is broken. So for one revolution of pinion D will give one jerk to pinion C. This jerk is responsible for periodicity. So for one revolution of pinion D will result 90/30, 3 times of 3 rotation. The 3 rotation here, B and C are connected in the same shaft. So B will also rotate 3 times. This is one rotation. So this was one rotation. Pinion D. Pinion C will be 3 rotation. Pinion B will have 3 rotation, and B and C, the ratio is 121:11. So there it will rotate 11 times more than A will rotate 11 times more than B. So it will rotate 33 times. So every 33 rotation, and A pinion is connected with the front roller at with the same shaft. So 33 rotation will be there for one rotation. 33 rotation of front roller will be there for one rotation of defective roller D. So for 33 rotation, 33 multiplied by pi multiplied by 25.4, and if it's millimeter, if we want to make it say meter, it will be 100,000. So the value is 2.63 meter. So in this way we can proceed. So you can see here, so from given gearing diagram, for one revolution of D, front roller will rotate 33 revolution, and front roller delivery is 2.63 meters. So the location of the periodicity will be 2.63 meter in the spectrogram. Now defective pinion F. Now let us go back to that diagram. F is defective. So rest other rollers are perfect. So here in this type of numerical, we must see the flow of motion. So the D being the drive source from
somewhere it's coming, it's getting the drive, and from D the pinion E is getting drive, so they are in the same shaft. From pinion E, which is perfect pinion, so there is no defect, which is driving the F, and F is also rotating uniformly because F is getting drive from E. But the drive which F is giving to G, it has got some jerk due to defective teeth at the, say, one tooth is say defective, so defective teeth, it is giving drive. So for one revolution of F, G is getting one jerk. So the ratio as the number of teeth for F and G are same. So for one revolution, G will get one jerk. So middle roller will rotate one revolution. So for one revolution, that is the circumference of the middle roller will be pi 23 millimeter divided by 1000, okay, and the front roller draft, front zone draft. This is the, so here whatever front, the wavelength is generated at the middle roller, that will be stressed by the draft at the front roller. So if we multiply by front draft, that we have already calculated earlier, so from there we can get the wavelength due to the defective roller F. So we can see here, so one revolution, so for one revolution the middle roller delivers 7.23 centimeter, and the front zone draft we have calculated 29.6. so if we multiply here, we will get 214 centimeter. So the defect location will be at 2.14 meter in the spectrogram. Okay, and third one, the defective back roller. Back roller is defective. So back roller, when back roller is defective, so for one revolution, that is eccentric, for one revolution it is generating one wave. So the wavelength at this point will be pi multiplied by 25.4, that's the diameter. So if we convert it to meter by 1000, and then we have to multiply by the total draft, because at the back zone, then after total draft the yarn is producing, it's producing the yarn. So total draft, if we, so this will be in meter. So let us see the value. You can see here, so back roller defective pi d by total draft multiplied by total draft by 1000. So this is the in meter. Total draft is 30, so it is 2.63 meter. And then the middle roller. So, middle roller defective that we have already seen, it is in same way. So, 23 millimeter diameter, so pi the circumference, and in centimeter divided by 10, so 7.23 centimeter is the circumference. So, the wavelength of periodic fault will be equal to the circumference. So, front zone draft we have already calculated. So, if we multiply, so this will become 2.14 meters. So, therefore, the position of the peaks of the spectrogram is 2.14.